This video will explore the concept of scatter plots. And going along with that will be correlation coefficients and coefficients of determination that describe the relationship between our variables. So let's get at it. What is correlation and regression all about? It's about looking at whether or not two numeric variables are associated. So in regression, there's an x and a y, kind of like in algebra, and they are measured on each subject. Each data value is a pair, an x comma y, and the graph of this pair is called a scatter plot. Then we want to measure how strong is that relationship. And there's a statistic called the correlation coefficient that does that. The sample correlation coefficient has the symbol little r, and r is always a number between -1 and 1. Here's our first scatter plot. It's quite simple. We're trying to decide if there's an association between height and weight. The x is often called the predictor variable, and the y is also often called the response variable. So we're looking to predict weight based on how tall a person is. As you can see, there's a scattering of points, hence our scatter plot. And I've identified one data point on the graph. This is a person that has a height of 56 inches and that weighs 79 pounds. So the way you measure whether the association is a strong or a weak association is using the sample correlation coefficient. StatCrunch will provide that for you. The formula is kind of complicated, so you don't have to worry about that. But we do have to worry about deciding how to describe a scatter graph, looking at a scatter graph and describing whether it's going to have a positive, negative, or zero value. Let's look at the positive correlations first. This is a perfect positive correlation. If you were to fit a straight line to this data, it would be all the data points would be exactly on the line, and it would have a positive slope. The next one is a strong positive correlation. The dots, the data values, are not perfectly on a straight line, but they are close to being on a straight line. So we're going to call that a strong positive correlation. The last one is a weak positive correlation. Yes, there's an upward trend, but a straight line would not fit all the data values very well at all. So you've got perfect, strong, and weak. Let's go down here. All of those were upward trends. We're down here with a negative correlation. So this is a perfect negative correlation. The value of r would be close to -1. A strong but not perfect negative correlation, it would be close to, r would be close to -1, but it wouldn't be -1. And here we have a weak negative correlation. R would be close to -1, but not strong enough not close enough to call it strong. So we're going to call it a weak negative correlation. So we have positive with upward trends, negative with downward trends. In the middle here, we have no trend at all. Not positive, not negative. So we would say that the correlation coefficient is 0 if it is completely scattered. So I want to present you with an example. The first example is going to be X is the weight of a vehicle in thousands of pounds, and Y is the miles per gallon. So here we have the scatter graph. Sure enough, the more a vehicle weighs, the less the miles per gallon it's going to get. The correlation coefficient for that is a negative 0.72. It's negative because it's a downward trend. You'll notice the slope has a negative sign. We'll interpret the slope in a minute, but this is the prediction equation. This is the linear equation of the prediction line. It's a y equals b plus mx. That's the way equations go, if you recall from algebra. Here's our second example. Manager wants to see if the number of salespersons he hires that work on a given day has any relationship to the sales in thousands of dollars. So here we have the raw data. He has anywhere from 2 salesperson working per day to as much as 22. And here are the actual data values for how many sales there were that day. And here is the scatter plot. Surely there is an upward trend. The points are pretty much close to the line. So this value here, this XY, is the number of sales persons that worked that day. And over here you have what the sales in thousands of dollars was. So we have an example of a positive and a negative correlation coefficient. So the truth of the matter is a correlation coefficient, to say that R equals a negative 0.74 or positive 0.94, that's hard to explain. You can only use words like weak negative, strong positive. We want something that is a little bit more to the point. Okay, so that's a new statistic called the coefficient of determination. It has the symbol capital R because it tells you more. How do you get capital R? How do you get the coefficient of determination? You take the sample correlation coefficient and you square it. And that creates a new statistic, capital R, called the coefficient of determination. Let me tell you abstractly what the coefficient of determination is and how it can be worded. What it does, it explains the variability in the response variable that can be explained by its linear relation with the explanatory variable. Well, we certainly need that applied to the examples that I presented with you earlier. In the example where the weight of a vehicle was used to predict miles per gallon, R was a negative 0.72. So when you square that, squaring always makes something positive, you get a 0.52. Okay, so what does that mean? It means 52% of the Y. 52% of what we're trying to predict, miles per gallon, can be explained by the linear relationship with the weight of the vehicle. So we were out to determine, is weight a good predictor of miles per gallon? Kind of, sort of. Okay. If you use the weight, you're only explaining 52% of the variability in miles per gallon. So what's the other factors that come into play here? Probably things like the make or model of the vehicle, the horsepower of the motor, whether it's driven on smooth pavement or rough pavement. All of those other things account for the other variability in miles per gallon. Our second example was on salespersons, and if they were a good predictor, number of salespersons, a good predictor of the sales in thousands of dollars. And we found there was a correlation coefficient that was very close to +1. So we'd call that strong positive. When we square it, we get a 0.885. What does that coefficient of determination say? Converting it to a percent, it says 85.5% of what we're trying to predict, which is sales in thousands of dollars, can be explained by the linear relationship with the number of salespersons working daily. So that is fantastic. The predictor variable, number of salespersons working daily, did a very good job of predicting sales. It explains 85% of the variability. What else might go into the variability in sales? Oh my gosh, maybe the location of the store, maybe the weather on those days. So it's not a perfect predictor of sales, but it's a very good predictor. So we've done a very quick summary of the kinds of information you can get from a scatter plot, the correlation coefficient, how to interpret those graphs, the scatter plots, and how powerful R is in expressing percent of variability in your response variable that was explained by your predictor variable. It's a lot. I hope you enjoyed this video, and I certainly hope it helped.